Today, we will be discussing how to calculate and prepare a buffer for use in the lab. Imagine that you find a laboratory procedure that calls for 100 milliliters of 500 millimolar Heaps buffer at pH 8.1. You look around the lab to find a bottle of it, only to realize that you need to make a fresh batch. If you're anything like how I was the first time I had to make a buffer, you may look something like this. But don't fear, because in this video, we will work through this preparation together from calculating what we need to actually making the solution. Before we begin, let's review some buffer theory. A buffer is a mixture of a weak acid and its conjugate base. It is used to maintain pH within a certain buffering range. Looking at the acid-base equation for Heaps, we see that Heaps is the acid and Heaps minus is its conjugate base. Using this information, we can implement the Henderson-Hasselbalch equation. This equation is used to derive the pH of a buffer system. Its general form is pH equals pKa plus the logarithm of the quotient of the conjugate base and weak acid concentrations. Specifically for our example, pH equals pKa plus the log of Heaps minus concentration divided by Heaps concentration. Now that we understand the Henderson-Hasselbalch equation, let's apply it to our example. We plug in the desired pH 8.1 and the literature value for pKa of Heaps 7.5. pKa values can be found in textbook tables or through an internet search. To solve this equation, we first subtract 7.5 from both sides. Doing this, we obtain 0.6 equals the logarithm of Heaps minus concentration divided by Heaps concentration. Next, we take the inverse log of both sides, finding that the ratio of Heaps minus to Heaps equals 4. This means that for every 4 parts of Heaps minus, there is 1 part of Heaps. We will think of this as 5 total parts of Heaps. Now that we have the ratio of the conjugate base to the weak acid for a generic Heaps buffer at pH 8.1, we need to find out how much of each of these we need to make 100 milliliters of our 500 millimolar buffer. First, we multiply the concentration of the buffer times the volume in liters to find out how many total moles of Heaps, that is, the sum of Heaps and Heaps minus, will be present in our solution. For our example, we need 50 millimoles of Heaps total. Now, we can set up ratios to determine the number of millimoles of Heaps and Heaps minus we need. Since there are 4 parts Heaps minus for 5 total parts of Heaps, we need 40 millimoles of Heaps minus. Similarly, because there is 1 part of Heaps per 5 total parts, we need 10 millimoles of Heaps. We're almost finished with our calculations. All that we have left to do is convert the moles of acid and conjugate base to grams. Heaps is available commercially, and Heaps minus is available as a salt, commonly as Heaps sodium salt. We simply convert millimoles to moles and multiply by molecular weight to find the grams of each reagent we need. Performing these calculations, we find that we need 10.4 grams of Heaps sodium salt and 2.6 grams of Heaps. Congratulations, we have all the information we need to make our buffer. Now it's time to step into the lab and make a solution. First, carefully weigh out the Heaps and Heaps sodium salt. Be as accurate as possible to minimize the pH adjustment later and ensure the most accurate concentration. Next, dissolve the solids in approximately 70% of the final volume of water. I suggest doing this in a volumetric flask or a falcon tube as appropriate for your volume. We use 70% of the total water so that if the pH needs to be adjusted in a later step, we will not exceed our total volume when we add acid or base. Once the solids are amply dissolved, we will check the pH using a pH meter. If the pH is too high, add hydrochloric acid until desired pH is reached. If it's too low, add sodium hydroxide. Once your pH meter reads the desired pH, fill your container to the final volume of water, mix well, and you're ready to use your buffer. Now, let's recap what we've done. We've reviewed buffer theory, calculated all the information we need to make a buffer, and walked through the protocol for actually making the buffer. We've gone from being puzzled by a problem to knowing exactly what we needed to make our buffer. Good job.